Chemistry and Chemical Warfare. Connection 1. Nuclear fission and the uranium bomb. Nuclear fission is the process in which a heavy nucleus splits into lighter nuclei. Uncontrolled nuclear fission is responsible for the massive destructiveness of an atomic bomb. The most familiar fission reactions involve the splitting of uranium atom. In these reactions, a uranium-235 atom is bombarded with neutrons. The uranium nucleus then splits apart into various product nuclei. Fission reactions produce vast quantities of energy. For example, when 1 mole of uranium-235 splits, it releases 2.1 by 10 to the 13 joules of energy. This above information is an application in real life, which is the atomic bomb. Example 1. The atomic bomb. Splitting the uranium atom. Uranium is the principal element used in nuclear reactors, and in certain types of atomic bombs. The specific isotope used is uranium-235. When a stray neutron strikes a uranium-235 nucleus, it is first absorbed into it. This creates uranium-236, which is unstable and causes the atom to fission. The fissioning of uranium-236 can produce over 20 different products. However, the product's masses always add up to 236. The following two equations are examples of the different products that can be produced when uranium-235 fissions. By the end of each reaction, energy is released, which is the energy released when a bomb explodes. This kind of bomb was used in the U.S. Army against Libya recently. This is a picture of uranium-235. Connection 2. The use of catalysts in the production of chemical weapons. A catalyst is a substance that increases the rate of a chemical reaction without being consumed by the reaction. A catalyst works by lowering the activation energy of a reaction by providing an alternative mechanism. Catalytic reactions have a lower rate limiting free energy of activation than the corresponding uncatalyzed reaction, resulting in higher reaction rate at the same temperature. Example 2. Phosgene is a chemical compound with the formula COCl2. It is a colorless gas that gained infamy as a chemical weapon during World War I, as it poisoned soldiers when it was thrown on them. Phosgene is produced by passing purified carbon monoxide and chlorine gas through a bed of porous activated carbon, which serves as a catalyst. The reaction is exothermic, therefore the reactor must be cooled. Activated carbon, also activated charcoal, is a form of carbon that has been processed to make it extremely porous and thus to have a very large surface area available for chemical reactions. In this case, the chemical reaction involves purified carbon monoxide and chlorine gas. CO plus Cl2 gives COCl2. The reaction is exothermic, so the reactor must be cooled. This is a picture of activated carbon, the catalyst used. Because of safety issues, phosgene is almost always produced and consumed within the same plant, and extraordinary measures are made to contain this toxic gas. It is listed on Schedule 3 of the Chemical Weapons Convention as one of the most dangerous chemical weapons. Although less dangerous than many other chemical weapons, phosgene is still regarded as a viable chemical warfare agent because it is so easy to manufacture when compared to the production requirements of more technically advanced chemical weapons. Connection 3. Oxidation and hydrogen cyanide. Redox reactions describe all chemical reactions in which atoms have their oxidation number changed. The term comes from the two concepts of reduction and oxidation. It can be explained in simple terms. Oxidation is the loss of electrons or an increase in an oxidation state with a molecule, atom, or ion. Reduction is the gain of electrons or a decrease in oxidation state by a molecule, atom, or ion. Example 3. Synthesis of hydrogen cyanide. Hydrogen cyanide is a chemical compound with chemical formula HCN. It is a colorless, extremely poisonous liquid. It can also be found as a gas. HCN has been used as inhalation, rodenticide, and human poison. Furthermore, cyanide ion interfere with ion containing respiratory enzymes. Hydrogen cyanide forms in at least limited amounts for many combinations of hydrogen, carbon, and ammonia. The most important process is the Andrusov oxidation, in which methane and ammonia react in the presence of oxygen at about 1200 degrees Celsius over a platinum catalyst. The energy needed for the reaction is provided by the partial oxidation of methane and ammonia, as shown in the equation above. Methane undergoes oxidation by losing 2 electrons, and ammonia is also oxidized. This is a picture that shows a flow chart that shows what happens if HCN gas is inhaled. It causes nausea, vomiting, death, etc. And that concludes my presentation.